Hello dear viewers, and welcome back to the video series on area moments of inertia. In the first part we focused on a rectangle, and in this part we want to show you how to calculate the area moment of inertia of a right-angled triangle. First, let's look at the underlying coordinate system. We have the y-axis, which is the horizontal axis, and the y-axis extends to the left, meaning that as you go to the left along the y-axis, your y values go up. Similar thing is present with the z-axis, which extends downwards, meaning that as you go down along the z-axis, your z values go up. And the black line, that line represents the area profile of the right-angled triangle. The width of the base is B, and the height of the triangle is A. And similar to what you did with the rectangle in the previous part, to compute the area moment of inertia with respect to the y-axis, you need to integrate this function over the entire area of the triangle. And to do so, you need to know that the infinitesimally small area element dA is the product of its height, which is dz because it's on the z-axis, and the width of the area element, and the width of the area element is basically the y value. And contrary to what we had with the rectangle, where the width was constant no matter what your z location was, with the triangle, we have a situation where the width or the y value is dependent on the z location. And to incorporate that dependence into the integral, you first need to establish a function of y with respect to the z location. And to do so, we need to resort to the linear function, which you covered in your high school in your later years. And as you remember, maybe, the equation of the straight line was y is equal to mx plus b. In this case, I have replaced b by c so as not to confuse with the base width of the triangle. So in your high school, you had b, but I'm just going to use c to avoid the confusion. And in a coordinate system where the vertical axis is the y-axis and the horizontal axis is the x-axis, so basically in a traditional coordinate system, the intercept with the y-axis is c, or simply this height at the y-axis, and m represents the slope of the straight line, and the slope is computed via dy over dx. In other words, the change in y over the change in x. You could also say the rise over the run, because the coordinate system in our situation, where y goes to the left and z goes downwards, because that coordinate system is different from the traditional coordinate system, we need to reformat the equation for the straight line. So in this case, the intercept with the z-axis, which is the dependent axis, while the y-axis is the independent axis, the intercept of the z-axis is c. And if you look at this sketch with the triangle, you will see that c is basically equivalent to a. A is the height of the triangle. I will set equal c to a. So the equation therefore changes into z is equal to my plus a. The slope m, as I said, that's the change of dz over dy, or in general, that's the change in the independent value over the dependent value. And you should know that to determine the slope, the intercept of the y-axis, where z is equal to 0, is b in this case, as you can see if you compare the pictures. And the rise over the run, in this case, would be basically minus a over b, y minus a over b, because as you go b steps to the positive direction along the y-axis, your z value decreases. So your rise is negative and your run is positive. And as such, your slope ends up negative. So m is equal to minus a over b, and the whole equation for c in the new coordinate system is thus minus a over b times y plus a. So that's your equation that expresses your z location as a function of the y location. And for our area element, let me write down the equation once again. I'm actually gonna do it here. I sub y is equal to the integral of z squared, and now dA is the product of y and dz. And since y, so to determine y, you have to rearrange this equation. And if you do the rearrangement, you will get y is equal to, let's see, z minus a, because the a is going to go to the other side, divided by minus a times b. And if we simplify it further, we will obtain b times a minus z divided by a. This expression can be simplified even further by writing y is equal to b times 1 minus z divided by a. And why do we need to come up with this expression? Because the area element dA is the product of y, the width of the area element, which depends on z, times dz. And the dependence of y as a function of z is expressed by this equation. So we need to insert this part into y. Let's do that. Let me first indicate that we're integrating over the area of the triangle. So the integral of z squared times y, and y is b times 1 minus z over a times the z. And to find the integral, we need to integrate from 0 to the height a. Be aware that this coordinate system has its origin at the top right corner, not in the middle or in the centroid, but at the origin, or basically where you have the right angle. And now let's try to expand that equation. It's going to be bz squared times 1 minus z over a times dz. I'm going to continue here. And that is equal to the integral from 0 to a of b times z squared minus, so now we need to multiply bz squared times minus z over a. And that's going to give us a minus b times z to the third power divided by a. And then you attach dz. And let's try to simplify it even more. Well, I'm not gonna try to simplify it more, not so much. Instead, I'm just rearranging the positions of the variables to make it look more eye-friendly. So it's going to be bz squared minus b over a times z to the third power. I think this looks more eye-friendly. dz. Well, not dz, I'm just saying dz. Okay. Now let's find the antiderivative of this expression. I'm going to use the brackets, the square brackets. So bz squared, the antiderivative, it's going to be 1/3 times b times z to the third power minus 1/4 b over a times z to the fourth power. And the whole thing needs to be integrated from 0 to a. So we're going to put 0 at the top, at the bottom right, and a at the top right. So you can disregard 0 because if you insert 0 into the z's, you're going to get 0. So we can just focus on a, on the upper value, and that's going to give us 1/3 times b times a to the third power minus 1/4 times b over a times a to the fourth power. And this a reduces the fourth power by 1. That leaves us with 1/3 b times a to the third power minus 1/4 times b times a to the third power, and 1/3 minus 1/4 times b times a to the third power is equal to, let's bring the denominators to a common number. We have 4/12, plus, minus 3/12 times b times a to the third power, and that is equal to 1/12. b times a to the third power. So this is the area moment of inertia of a right-angled triangle with respect to the y-axis when your coordinate system is at the right angle of the triangle. And just be aware that in some tables the area moment of inertia will be different than 1/12 times b times a to the third power, and that's because in some tables the reference coordinate system does not start at the right angle at the top right or just at the corner. The coordinate system has its origin at the centroid. So, as I said before, pay attention to the underlying coordinate system or the underlying origin of the coordinate system of the value that you're looking up in the table. And to find the area moment of inertia of a rectangle with respect to the z-axis, your steps will be analogous. So you have to integrate over y squared, and then you have to integrate over the whole area. And I'm not gonna work it out throughout because it will be too time consuming if I did that. I will just show you that in that situation, if you are looking for the area moment of inertia with respect to the z-axis, so I'm gonna write down your area element would be this strip. Well, that's just an example. Of course, I could have placed this strip somewhere else. I'm just gonna give you an idea of how this strip looks like. And that strip is a vertical strip with the width dy and the height z. And the equation that you would need to use is this one. So integrating over the whole area of y squared times dA, and then your dA is equal to z times dy and your z will be basically this equation. You would plug this equation into z and compute the integral analogously to how you did for the area moment of inertia with respect to the y-axis. And if you do all these steps, your final result will be 1/12 times a times b to the third power. At last, let me tell you that if you have a shape of the body that is not a rectangle, basically a shape where the y location depends on the z location and vice versa, You always need to come up with an equation that expresses one coordinate as a function of the other coordinate. And then you plug that function into the respective variable that is standalone. So y in this case and z in this case. Thank you for watching, and I shall talk to you soon.